So far we have discussed about the contents wise. We can see we have discussed about the characteristics and description of the light in our previous classes. We have discussed the certain uncertainty principles for the photons and the properties of the beams and properties of the photons. And now in today's class we are moving towards the geometrical optics. Okay, so today we discuss about geometrical optics. Or sometimes also called ray optics. So geometrical optics or ray optics. So I think this is very useful to design any optical system and for a better understanding. So mainly it describes the light propagation in terms of the rays. So now in this method we will take the light beam as a ray, as an optical ray. So thus the ray in the geometrical optics is in just abstraction which is useful for approximate the paths of the light and its propagation under some circumstances. Like for example, if you have a medium, different medium, how it propagates, and if you don't have a medium, how it propagates. Okay, so this is just for a better understanding how the light propagating in the space with the different conditions under different circumstances. Okay, so in this ray optics there are certain assumptions. So the first assumption is light rays propagate in a straight line. Okay, so that means the light ray propagates in a straight line path as they travel in a homogeneous medium. Okay, so that is one of the assumption. The second assumption, the ray bend, so that's the bending nature of the light, bend, and in particular circumstances or in particular conditions, it may split. So the light at different conditions, it may split or it can bend. If again, if the splitting beams will combine together, they may interfere in a different medium. So all these are part of the assumptions. And the third one, it follows the curved paths in a medium. It follows a curved path in a medium in which the refractive index changes. So the refractive index represented as n, it changes. Okay, so depending upon the refractive index in the medium, the path of the beam or a ray will change. So it can make the curved paths. So this ray may be observed So ray can also be absorbed by the medium or reflected. It can be absorbed or might be reflected. So the light ray so is propagates in a straight line path. So that's what the assumption is made. So we know that so the propagation of the light is one direction, it needs to perpendicular direction the vibration of the fields. So for example, now the curve that is taking is perpendicular to the light wavefronts. So for example, you talk about the Fermat principle. So the Fermat principles will tell you so this Fermat principle will tell you the path taken between 2 points. For example, this is point 1 and this is point 2. Okay, the ray of the light, it takes the minimal time to reach the point P2. So for example, this is the path it is taking. Okay, so the time it takes is T1. And now you tell me what happens if this path it takes light. This will be T2. So your T2 should be greater than T1 because it covers a large distance. And similarly, in other direction, which is comparable to the T1, that is T3. So now the light propagates between these 2 points, which is the shortest time, the least time it can travel. That is the direction, or that is the path direction of the light. That is the T4. Now T4 is the shortest time it can take light from P1 to P2. Okay, so that means this is the Fermat principle. So what in the geometrical optics we follows the Fermat principle. So we always assume the light travels in a shortest time. So it takes the path which can reach in a shortest time from one point to other point. So with that, we are able to explain loss of reflections and loss of different optical laws like refraction and Snell's law. Everything we are going to explain with this on the basis of our Fermat principle. Okay, so now we will talk about different optical components and how they behave and what happens when the rays of light are propagating through this optical medium, what kind of a changes you can see. Okay, so for that we will go to one of the simulator, the ray optics simulations. I'm just opening the ray. You are able to see, right?
Yes.
Yes, sir.
Okay, so now I'm taking a ray. So this is the source, it's emitting the light. So now you see you always take any point, so it takes the straightest path. For example, I will take a ray to go to this point, it go this direction. So it takes a minimal time, the shortest time it can take. So now I will take a beam of the light. So now this is the source which is giving me a beam of light. Okay, so the beam of light is propagating like in a ray. So whatever I'm representing in this is a ray optics diagram. Okay, so this is the source which is delivering the light. Okay, and you, as you see here, these light rays are propagating in a straight line. And now I will introduce different optical components. So now tell me, what are the optical components you know? So what are the optical components you talk about? Different optical components. Yes. Hello. So what are the optical
Yes, sir.
components you know about?
Yes, so like mirror,
Yes,
lens,
Okay,
mirrors,
aperture
so
slit, so
we'll talk about mirrors. Okay,
Fibers,
next
fibers,
fibers. So next
lenses,
lenses. Next,
aperture slits,
so aperture
Prisms,
slit,
prism,
prism.
pole,
Sorry.
various sources, LED sources, laser sources,
Okay, light sources. Yes, someone
polarizers,
tells polarizers. Next,
detectors, detectors,
detectors,
collimator,
collimator. Okay,
telescope and microscope. And
telescope, microscope.
So should we include our eye in human eye in optical components or not?
So you talk about the detectors. So detector is a broad term, so it will cover all. Your eye also will be part of a detector.
Yes.
Okay.
grating element, grating element as well,
Y-
and different
Yes,
type of
grating,
solutions, and different type of solutions
grating.
which can reflect
Biaxial
the
crystals, that is
refractometer.
quarter wave plate, half wave plate.
Yes. So wave plates. Okay. Anything more?
And different type of solutions which can
Uh,
reflect light.
Different kind of a solution for refraction, right? So that can be part of the any of these things. See, for example, lens is also a kind of a material medium where it can refraction also happens. Without those refractions, you are actually getting a lensing, right?
yes,
Okay,
sir.
so that's why I'm not writing this solutions. Any other optical components?
So why is telescope in? Because telescope is a type of lens itself.
Yes. So now my question is, I'm talking about optical components. So now you have to find out what is the optical components. So the basic components you have to discuss is mirror, lens, a prism, a polarizer, a grating, wave plates. So now what you are talking about, this
Glass slab.
collimator is actually a optical system. Okay, so this collimator is combination of the lenses. So you can actually talk about, so that is a optical system. The optical system is made up of optical components. Similarly, your telescope is also an optical system. You can design different telescopes with the combination of different optical components. So your optical components are the basic units to make your optical systems. Similarly, the microscope is also a optical system which has combination of different optical components. Now coming to aperture, so this is a optomechanical component. Okay, it's optomechanical component. So that means this is actually having a mechanical arrangements in your design. So aperture you can define what kind of a size of the aperture, because it's actually a free space between in your, for example, you talk about aperture. So you have a aperture like this, and then now in your aperture what you have, you can actually the variable, so you have a variable knob, so that with this variable knob you can actually open this aperture and close the aperture. Close the aperture means you have a minimal optical path can travel. That means the light intensity you can control with this aperture. So now what I am seeing here, so this is actually is closed, it's blocking. Now once you rotate this knob, so that what happens, so this can be opened up to whatever the maximum it can open, right? So that you can vary the size of the aperture. So it's a mechanical component. Generally this is called optomechanical component. Similarly, the slit. And coming to light sources, so this is the combination of your optical components and electrical components. So everything, this is completely it's a separate category. So it's a light sources, that is generally source, and this is the detection. These two are called sources and detection. Okay, and the fibers is also a part of the material medium. Okay, sometimes people can also call as one of the optical component. So this, depending upon the designs, you can call this as one of the optical components also. Okay, so these are the whatever the yellow ones, I made it as a optical component, and there are few like beam splitters. Okay, so this beam splitters, that means it can split the beam into two beams. You take one beam of light, it can be split into two beams depending upon how much transmission and how much reflection, depending upon the design of the beam splitter. Okay, so now today we will see when rays of light going through some of the optical components, what are the things you can observe. Okay, so that we are going to see. So now, so this is the collimated beam. Okay, whatever you are seeing here is the collimated beam. So now I'm using a mirror. Okay, now I'm using a mirror. I'm placing the mirror. So now what you see, the mirror is reflecting all the light which is incidenting on it in exactly opposite direction. Now what happens if I rotate the mirror? If I rotate the mirror at different angles, I can actually guide the light beam where to travel with a given angle of incidence. So you can adjust your mirror position, okay, to maximum it can. So that means, see, for example, with a given size, whatever we have taken the size of the mirror with the given beam diameter, you have access to up to this angle, roughly maybe you can say 120 to 140, and similarly you can do it for a other direction also, right? So you can control, or in this mirror you can guide the beam, your light beam, to travel whatever the direction you want. You can see, if you remove the mirror completely, so then it's out of the beam path. Now you can actually guide your light beam wherever you want. For example, now if I want exactly the light beam perpendicular to the incident light. Now if you see, if I place the mirror at 45-degree angle, if I place the mirror at 45-degree angle, you will see the light beam can actually propagating this rays are exactly perpendicular to the incident rays onto the mirror. Okay, so with the precise angle, you can actually control the beam path in terms of the rays we are talking about. So the light rays, which direction you can travel, you can actually precisely control using this mirror. So the mirror is designed for a different electromagnetic radiations. So these mirrors having different coatings on it depending upon the refractive index of the medium, dielectric medium. Accordingly, it will allow those wavelengths only to reflect. For example, if you want a visible light to reflect, okay, so right now you are talking about visible light. If you want to visible light to reflect, the aluminum mirrors, that means you have a aluminum coating on this on any of your flat substrates, then what happens, your aluminum can reflect almost 92%, 80 to 92, 88 to 92% of the light will be reflected. If you want more reflection, you have to get a good material to coat on the your mirror substrate. So generally the substrate used as a just glass. On the glass they will coat either aluminum or a silver or a gold or different dielectric coating, so that you will get achieve highest percentage of reflection. Okay, so that is about the mirror. Now the mirror now it exactly is a exactly a flat mirror. So this generally you call a plane mirror. For example, now you take a mirror with a certain curve direction. Now, as you see here, now this mirror is reflecting. Now, what exactly happens? You see, as I change this mirror, you can see what exactly happening. So now also I can increase the ray density. So the number of rays inciding onto your mirror. Now as you see, so you can make a complex mirror. So now if you see actually the light is actually incident on this part of the mirror and focusing here, and then again after focusing it is defocusing and they're incident on the another part of the mirror, then again you have a reflection, then you can actually design a complex mirror like this. Or if you use like this, you can see you have a rays of light coming like this and your focusing of the mirror is here and again defocusing it. Okay, so that focusing positions you can actually control with the shape. Okay, you can see the focusing position is changing as with the curvature of your mirror. So that is actually the curvature, the radius of the curvature will decide the focal position. The focus is nothing but the concentrating all the rays at a given point. So where at that point now all these light rays will be concentrated, that gives your high intensity beam. Okay, so this curvature you can it will decide you the position of your focus. Okay, so then with the alignment of your different angle you can also decide the where you want to focus. So this kind of a mirrors will give you access to where exactly focus. So not only lenses, you can also use curved mirrors for a focusing. Now there are certain advantages and there are certain disadvantages. The advantages are, so when it is propagating through a lens, you have dispersions. But in the mirror, in generally in the metallic mirrors, you have reflections where your chromatic aberrations, different aberrations through your optical lenses can be eliminated using this kind of a mirror geometries. Okay, so this is about your mirrors. So how mirror will be utilized in the optics. So I think you are able to understand, right? Any questions so far? Is my voice is audible?
Yes,
Yes,
sir.
sir.
Yes, sir.
You
Okay.
Yes, sir. So as you said, like using mirrors, we can remove chromatic aberrations.
Yes.
So can you explain that?
Not all the mirrors, but the metallic
That is
mirrors.
how we can that is how
See,
we can
what is
remove
chromatic aberration?
mirror. Like there is some that is blurriness in color. That is if there is proper color is not visible. So a
No,
mixing of
that
colors,
means
I
that
think aberration.
that different wavelengths having a different focus because of the traveling through a our lens, right? So, for example, you have the lens. Now, what defines the focus? So, when the light ray inciding on the front surface of the lens, then you have to follow the laws of refraction and reflection, right? So when it is refraction, depending upon refractive index of the this media and different refractive index of this media and refractive index of this media will decide you the bending of the light, right? So now when light propagating through a medium, different wavelengths experiences different refractive index because your refractive index is not constant. Refractive index, when you talk about refractive index of a medium, for example, if you say for the glass, what is the refractive index of the glass? 1 point,
1.6.
roughly 1.5, right?
1.003.
1.5.
Right? So you are talking about refractive index of 1.5, that is actually not for all the electromagnetic radiation. In principle, your refractive index is wavelength dependent. It is not an exactly fixed value. So whatever you are talking about, mostly in the visible light, it is around 1.5. Okay, but not that it's exactly 1.5. So now when it's propagating through, if you have different wavelength components, when it is propagating through, so now what happens? The different colors, for example, now this is in blue color. For example, now I'm just for visual understanding, I'm giving a different colors. So now what happens here, when they focus, so for example, this is the focus for the blue light. So now the green light focus, because now I'm taking green light at the optical axis, you take somewhere away from the optical axis. Now the focus of the green light is maybe this position, and the focus of the yellow light, for example, at this position. So now, as you see, the different focal positions by different wavelengths. This is one focus position, this is one focus position, and this is one focus position. Now you see the different colors are focusing at different positions because it is traveling through a medium where medium is giving the light wavelength of the lights are experiencing different refractive indexes. Because of that, the whatever the image formation you're talking about at a different positions. Now image at different positions, what happens? You will see a blurring effect. Whereas in the metallic mirrors, now there is no propagation of the light through a optical medium. It's depending on the Fresnel coefficients. You have percentage of the reflection changes, but all reflect at the same time. So your focusing position is almost coincidence in all the colors. So that actually will reduce your the chromatic aberrations. Okay, so I'm not talking about here the cost of the things. So whereas if you, because there are a lot of things to be matter, these are very cheap. The lenses will be, you can buy in 50 rupees or 100 rupees, where a worst mirror in the laboratories you have to pay roughly 2000 rupees. Okay, so depending upon your experiments, you will choose which one is where you don't worry about the chromatic aberrations. So there you can use your lenses. Depending upon your experimental things, you can choose accordingly. Okay, but everyone has their own advantages and disadvantages also. So the alignment of the lens is much easier, whereas the alignment of the mirror will be little complex than the lenses. So now we move to the lens. Okay, so right now I'm talking about just the ideal lens. Okay, so now you see I just placed the ideal lens. So the ideal lens, as I mentioned, it doesn't have any aberrations. That is the basic idea of the ideal lens. So now you have a collimated beam incidenting on the lens. So when a collimated beam incident on the lens, it will try to focus depending on the focal length of the lens. So this is your focus position. So actually you can take the ruler, you will know what is the distance from the focus. Okay, so now as you change the position of the lens, you will see how the divergence of the beam. Okay, so now in this case, this is roughly the lens having a focal length of 100, depending upon the units what you talk about here. Okay, depending on the scale here, according to that units will be there. Okay, you can also play with your focal length. I can also extend this ruler. Okay, now you change your focal length. If it is a negative lens, that means what is meant by negative lens? Negative focal length. So you have two kinds of lenses, right? One is convex lens, another one is
Concave lens.
concave lens. So now the negative focal length lens means it's a concave lens.
Concave lens.
Okay, so when it's concave lens, what happens when it is concave? It will diverge the beam. If you see it's negative lensing, your beam is diverging. As you increase the negative, you see that is your acting as a diverging lens. Now it's a positive lensing, that means a convex lens. The focal length is positive. So now as you see, however you keep your focal length change, if it is longer focal length, that means from your lens position to your focal position is around 559 units, may be in the centimeter or millimeter, depending upon the dimensions of this background. Okay, so you can change with the different lenses. If it is short, if you use a short focal length. Now if you use a short focal length, for example I put 5, it's a short focal length, your focus will be tight focus and the divergence is very high after focus. As you increase your focal length, you increase your focal length of the convex lens, your divergence, still these are in the tighter focus conditions, still you can see the divergence is longer. As you keep increase the focal length, your divergence after the focus will reduce. You can see here like this. As you increase the focal length, you are actually shifting the focus wherever you want. So that means you can actually design with the geometry of the lens. Okay, so with the geometry of your lens, you can actually set where you want the focus is. Okay, that is the design of your optical components. Okay, so now for example I use 100 mm or a focal length. So now this is focusing here. So now for example I want to collimate this beam. After focus I need a focusing condition. then I want this rays to be also a focus. That means I want a collimated beam. So I will use one more lens to collimate the beam. So now I will place this one accordingly, such that you place your lens. So that means, see how you collimate. You take the one more lens, you try to bring the lens. Now you observe as I am moving the lens position, you will see different configurations. For example, I want one more focal length in the focus. I can get the focus here, or I don't want that. I want a collimated beam. So I can get a collimated beam like this. You see this beam, whatever is the size of the beam here, I able to achieve the size of the beam in the and after the long distances. It can travel in a collimated way. So now using two lenses, I can create the high intensity region that is called a focal region, and after that I'm also able to get a collimated beam. So with the combination of the beams, you can actually, with the different optical components, you can design your optical system the way you want. For example, I want, this is my beam size, I want my beam size bigger. That means you want to expand the beam size, or you want to down collimate the beam size. That means you want to reduce the beam size. Using the combination of the lenses, you can do that. But you have to do this kind of a simulations so that you can understand how the beam size is changing. Okay, so but you need, for that you need to have a combination of the lenses. You have different combination of lens, you have to play with it, then you may get the different size of the beams.